minutes. um, Thanks for waiting for so long, but now we are starting. Okay. Let's get started with a few announcements. Exercise 2 is done. Thanks everyone for submitting it yesterday. They will be graded and released to you soon. I haven't checked with Evgeny about his schedules afterwards. Well, we actually have quite a bit of time until the recap session, so yeah, I'm not sure how much time he wants to have for grading the exercises, so I'll check and let you know. For exercise 3, it's now available. He's in charge, Balint is in charge. There will be an introduction session after the lecture today. Okay, and then we are resuming the lecture on 15th of January. Yeah, yeah, alles gut. Vielen Dank. So, happy Christmas. So we received the survey results yesterday. So thanks everyone for filling in the survey and giving us feedback. So there was some new feedback that didn't come during the Google Forms survey. So there were some requests for making more structure in the lecture and presenting more high-level motivation and so on for the materials. So fully taken, and I'll try my best to have more structure here. And also you asked for more less monotonous presentation. I'll try. For the exercises, I see that quite a few people hate Google Colab, which is what I heard through Balint as well. So, but there is no quick fix for that. So perhaps from next time, we'll try other solutions. We are actually having a conversation about that already. Some people say it's too lengthy, too much resources, and you spend a lot of time on this. Yes, we will improve it, but exercise 3 is already there, so maybe you have to still try exercise 3, but next time we'll make it better. Yeah. And upload recordings promptly. We'll try our best to do that. And thanks again for the feedback. And let's get started with part 3, uncertainty then. Okay. So I was part of a company before joining the university, actually, called Naver. And when I was working there, I've found a lot of people, especially working in products team, coming to me personally, or I heard a lot of stories where product team comes to research team and says, why don't you implement uncertainty estimation module? Isn't it quite simple to do that, right? But we always say, yeah, but if you go into all the details, it's not so clear how to make it do it well. So I saw that there was quite some gap between what people expect from machine learning models and what people think is quite easy for machine learning models and what is quite hard in practice. And being on the side of research, I see that all kinds of reasons why uncertainty estimation could be so hard research-wise. So yeah, let's dig into why it is hard, and also definition-wise, it's really hard to define what you mean by uncertainty in the first place. So let's probably get started with what we exactly mean by uncertainty and why do we need this. Uncertainty estimation is a very critical building block in many applications, in particular applications that have human in the loop. You can think of it as a kind of one of the basic communication tool between machine learning models and humans. One of the critical communication factor between these two entities is for the models to express, I don't know, right? The model cannot know everything, right? And in those cases, you typically want humans to come in and do the task instead. And there should be a clear signal for that. And that's what uncertainty estimation is doing. So one can characterize this as a kind of a big pipeline which involves machine models and maybe some computer code, right, for doing simpler tasks. And sometimes human in the loop as well. And you need to have a better communication between all these modules. If you just have prediction results between these modules, then you don't have a good control over which module is taking over which component in which cases, right? So if there's a human you wish to kind of make them understand, now you have to come in and do something. So instead of just having prediction results in between these links, you also want to have some uncertainty associated with the prediction results. And that really makes the communication much richer and introduces a lot more possibilities. And also you can use these kind of automatized machine learning systems for risk critical applications as well, because that allows you to do risk avoidance as well. So I'm going to give you a bunch of examples of when we need uncertainty estimation. So one is image search for products. It's not a safety critical application, but you get annoyed when the results are not good. But sometimes it happens that users do not take photos in the right way. They just trust the system so much that they don't take a good contrast, good lighting condition pictures to send to the server. And you're not going to get very good search results. But if the model can tell the humans how you can take the photo much better to get better results, then that's also going to make the user happier. So that's one example. The other example is when your system has multiple modules. For example, object detection pipeline used to contain typically two stages. So the first stage is for detecting everything inside an image. That is likely to contain some object. And then the second stage is assessing for every they are called proposals for the objects. For every proposal, what is the class of this proposal? And then do a bit of adjustment of the box to have more precise, tight bounding box around each object. So this is a typical two-stage system, two modules. And between these two modules, there's not just the bounding box predictions, but also the likelihood of the bounding boxes or the uncertainty estimates for each bounding box. So you extract all the likely objects, but you also attach that with some scores, telling the second stage what is worth looking at this object. Okay, so based on this, you can, for example, do thresholding to only look at the most important bounding boxes. Now, there are some examples of high-stake decision-making as well for diagnosis, medical diagnosis, for example. Yeah, of course, you wish to kind of reduce the human load for diagnosing certain diseases by using machine learning models. But you also wish to know when the model is not so certain that for those samples, human doctors really need to come in and give some expert knowledge, right? So instead of just model outputting predictions, you also want some confidence measure, and you wish to threshold on top of that. Yeah, so you can also, yeah, this is like degrees of severity of the mistakes, basically. So let's say if the healthy person got predicted healthy, then you don't lose anything. But if diseased person gets prediction as healthy person, then there's a big loss that incurs for the person and for the society and so on. So in those kind of cases, you ideally you wish to kind of have the model abstain from making a prediction, and then you don't actually lose too much. Self-driving cars are like healthcare and self-driving cars. These are two most important, most cited high-stakes applications. The other one is financial, actually. But anyways, for self-driving cars, they also run into all kinds of problems because of distribution shift. You cannot get your self-driving car prepared for any kind of city. So when there's a data set distribution shift, ideally you want the model to abstain from making predictions because you don't want to trust the system too much in those cases. The other case is the model is encountering totally new observations that it has not seen before. So again, for medical diagnosis, there are certain categories of diseases that the model has been trained on, but maybe you want the model to still say, among the categories that I know, this is something that I don't know yet. This is potentially something that's a new class, and so maybe the doctor has to come in and maybe define this new phenomena as a new class. In any case, I can't make a decision here, right? So this is another example of open set recognition. So there are certain bacteria types, right? And let's say the discovery is still on progress. So every year there's going to be new species of bacteria that you have to, you get to know, right? And that means every year you're still going to see a lot of species of bacteria that you haven't seen before. In those cases as well, you want to have the ability to tell, yeah, these are actually new classes of a bacteria that I have never learned before. So by the way, all these slides are based on this, this nice tutorial slide from Balazs. And yeah, highly recommend it, actually. It's really good. Another example is active learning, right? You want to optimize your time spent on doing annotations, right? And if you look at training data sets for machine learning models, like 90% of them are very easy, and only 10% of them are more relevant and contains meaningful information that's going to help your model training. So ideally, you want to spend more time on those kind of corner cases rather than spending 90% of the time on everything. For determining which samples are worth annotating, you can also use uncertainty estimation techniques. So in the first batch of training, you train your model, and then for the next incoming data, you can determine which ones are the ones that the model tends to have hard time, right? And for those ones, you want to spend more time for the next batch of annotations. Another example is machine learning applications when you have to do exploration and exploitation. Active learning is a good case of that, actually. So you want to annotate, well, it's more like you let the agent go into the real world and then learn it by itself, right? But the agents also can determine which ones to experience, right, basically. So the agents wants to experience new experiences, right, given kind of limited time. And so you want to also optimize the exploration experience for the agent. And the typical way you do that is by using uncertainty estimate. So if the model is predicting something uncertain for certain samples, then most likely that's the region when the model will have hard time. So you probably want to make the agents have more experience in that regime. So this kind of logic is used in, let's say, Bayesian machine learning, Bayesian optimization, and which has all these kind of application scenarios. So there are discrete optimization problems where machine learning is used still, and there you probably want to maximize your experience on hard samples. In summary, confidence estimation is needed typically when all the outputs cannot be treated equally. You want to treat some of the outputs more importantly or with more trust, or pass it to the next stage, or pass it to some correction mechanisms like human in the loop. Of course, it's not needed when the model is perfect, and we know that the model will be perfect in the future. But if it's not the case, then it benefits to have some estimate of how uncertain the model is. Okay, so with this, we move on to the definitions and evaluation. For defining uncertainty, what is really important is to have a clear set categorization of two sources of uncertainty. I think we, in the uncertainty estimation community, we all sort of agree that there are roughly two big sources of uncertainty. So one is, I don't know because I have not experienced it before. And two is, I don't know because either of the answers are good enough. There are two good answers to it. So one is called epistemic uncertainty, and the other one is called aleatoric uncertainty. We will go into the examples and definitions in more detail. Epistemic uncertainty means I don't know because I have no experience before. So this is closely linked to Bayesian machine learning framework. So in Bayesian machine learning framework, you have some prior of the word knowledge, and then you gather some experience or data, and then based on that, you update your previous knowledge about the word, and this continues on and on. So as you have more and more data about the word, you have better knowledge and you have more precise knowledge. And that's going to reduce your epistemic uncertainty if you have more experience. Okay. So the state when you don't have any experience is when you have the highest epistemic uncertainty. And as you gather more data, you're going to have less and less epistemic uncertainty. So this is the typical setting where you can quantify epistemic uncertainty quite well. So let's say the training data looks like this. So you have two classes, red and blue. And you train some models here, right? So the theta 1, theta 2, theta 3 are each of them are linear models trained on the training data, red and blue. And each one of them is totally plausible because each one of them will give you 100% training set accuracy. So if you train with a loss function which strives for 100% training accuracy, any of these models are good. Okay. Or you can have a very different hypothesis class between all these models, and all of these models are still giving you 100% training accuracy. So this means given some limited data, you can always have very diverse answers for your model. And that's the source of epistemic uncertainty, because now there is a region when you did not cover during training, like these regions here. And for these regions, you're not going to have data. So your posterior will have higher variance. So this is the posterior, right? And this is the prior, and this is the data term, right? Because we do not have much data here, there will be less information to make this decrease the entropy here. And so the model variance here would be very high, okay? To reduce this, you can introduce more observations here. You can have more data on this region, and that's gonna narrow down the possible set of models here. So let's say you have some more reds here, some more blues here, then that's going to rule out, for example, theta 3 and theta 1, right? Because they will not anymore get 100% training accuracy. So now then you have less variance, okay? So this is also closely linked to active learning. So in active learning, you also wish to gather more samples from these underexplored regions, and that's going to reduce the variance for your posterior. Okay. Some examples. So when the distribution shift takes place, that's a typical scenario when you have epistemic uncertainty. The model has only seen scenarios when it's driving in the daylight, and suddenly it's driving in the night, and you have greater uncertainty at night because you have not experienced it before. Okay. The novel concept example also falls into the category of epistemic uncertainty. You're kind of looking at the region of no experience before. So that was the brief overview of what epistemic uncertainty is doing. We will go into further details in the next lecture, so I'll stop here for epistemic uncertainty. Now, allegoric uncertainty means I don't know, because there are multiple plausible answers. Okay, so let's assume a predictive task, P of y given x. So given an image, for example, you want to detect which classes are there. Allegoric uncertainty means the ground truth y given x is not a single prediction. It's multimodal, actually. Okay. What does that mean, for example? So this is the CIFAR dataset, and CIFAR dataset actually has 32 by 32 pixels for the images. So it's supposed to be very low resolution images, anyways. But for certain images, you can still see the object pretty well, like airplane and cat, right? And then human answers to these images will be highly unimodal, meaning that people generally agree that, yeah, this is an airplane and this is a cat. But for some of the other samples, people are very much confused what this object is. Some people say it's cats, birds, yeah, or sheep, yeah, for this image. And so if you look at the distribution of human answers, P of y given x is actually not a one-hot vector for this one as well. So this is the case when you have very high allegoric uncertainty. So allegoric uncertainty is typically known to be the case when you have some corruptions in your input data. But I wish to tell you that that's not the only case. There are many phases of allegoric uncertainty here. It comes up in ImageNet classification task, for example. As you know properly, ImageNet classification task is a single class prediction task. Given an image, give me a single label corresponding to this image. But actually, ImageNet classification has 1,000 classes. And so it's very likely that a good portion of the ImageNet training samples will contain more than one ImageNet classes, because there are so many classes. So for example, in this image, the final label in the ImageNet training set is desk, right? But actually, there are so many other objects that also correspond to one of the ImageNet classes, like screen, monitor, coffee mug. These are all in the image, and these are all part of the ImageNet 1000 classes. So in other words, the ground truth y given x in this case is multimodal. And in principle, annotators will arbitrarily choose one of these classes to annotate it. Okay. Yeah, this is a typical example. I just put some random numbers here. So 50% of people will say this is a rabbit. The other 50 will say it's a duck. So this is a typical confusing case for humans. So it's a little different from here, right? In here, we know that for sure there are certain classes, right? But the choice of among these classes is arbitrary. But here, the perception itself is perhaps arbitrary. There are some differences here. And this is another example of having some corruptions in the image. So let's say there's a random cropping of an image from MNIST. It's called two-digit MNIST, right? And let's say there's a big chunk of pixels removed from the first digit. Based on the bar, like small white thing in the bottom, one could say, yeah, this is perhaps 17 or 47. Or it could actually be in also 97 actually, because 9 also have a bit of bottom part as well. So for these kind of samples, you can also set the ground truth probability for 1747 and 97 with some non-zero probabilities. So in general, when there's a feature missing, right, even if the latent truth is well separated, by removing one of the axes, one of the features, you may introduce some overlaps in the ground truth classes in the observation space. That's when you have also allotric uncertainty. And yeah, measurement noise is coming from all kinds of sensors. Like image sensors are known to introduce blurs like motion blur, noise, low contrast sometimes, and then of course if the resolution is super low, like in sci-fi case, you don't see the object super clearly. Could happen when you crop some of the borders of the image, or content-wise, when there's an object occluding the other object in the background, then you don't know what's happening in the back, right? Or you wish to kind of recognize who the person is based on the back view of the person, then you also don't know for sure who the person is. Okay. Other types of sensors suffer from it as well, like microphones, EEG signals are known to be notorious for high sensor noise as well, and space telescopes. Yeah. Or maybe the task itself is multimodal, right? This is typical for generation task. When you ask the model to generate an image based on some text prompt, there is no single good answer. There is actually a distribution of good answers. This is in principle also one case of allotric uncertainty. Language models as well. When you have the first part of the sentence and ask the model to complete the rest of the sentence, that's also high allotric uncertainty task, right? So the question is when we can reduce, whether we can reduce allotric uncertainty at all. We can reduce the epistemic uncertainty, right? If we have more experience, especially if we sample more from undersampled regions in the input space, then we reduce the uncertainty there. But when P of y given x is multimodal in the first place, the more you gather samples for those corner cases when your y given x is high, you're only gonna still get some mixed supervision, right? You're gonna have more n, right? More number of samples there, but still the distribution of y will be mixed. So adding more data will not actually reduce the aleatory uncertainty. So eventually, to address this aleatory uncertainty, there's be some design strategies for the model. For example, we have to formulate an architecture which is accommodating multiple plausible predictions. And we maybe have to alter the optimization strategy for the model to encourage diverse possible answers rather than sticking to one confident, one most likely answer. So yeah, we will talk about that in lecture 11 actually. So with this, yeah, this is yet another example of aleatoric versus epistemic uncertainty. So you see, like, what is this, right? This is when you have mixture of two classes in the ground truth, right? For those samples in the training set, you're going to have two different types of classes to train. So this is aleatoric uncertainty, and this is the case when you don't. Your test sample is from a low density region in the input space, and so there are multiple plausible classifiers here. So this is epistemic uncertainty. So this is another example from semantic segmentation. So yeah, pretty old paper. Give an input image. The task is to generate something like this ground truth. So for every pixel, you wish to say what is the content of that pixel. And of course, your final prediction is not perfect. So it makes sense to have a good estimation of uncertainties for each pixel. And actually, this is the heat map telling you how much uncertainty the model has for each pixel. And there's a good separation of aleatoric uncertainty and epistemic uncertainty here. Let's zoom into one of them, actually. So if you look at this image, the model tells you it has higher aleatoric uncertainty around this region here and here. So if you look closely, it turns out these are actually close to the branches of the tree. And this region when you have a lot of mixed objects, right? It's very far away from the camera, so you don't have good resolution here to tell apart. And so for those kind of typical training samples, you'll probably have seen a lot of label, like mixed supervision. So for the same kind of pixel, a lot of people will annotate it differently. Some of them will annotate every small pieces of branches here as part of tree. Some of them will not care too much and just paint everything as sky pixels. In that case, you're going to have high aleatoric uncertainty. And then later on, when you see a similar kind of type of like pattern, right, with the mixture of branches and trees, and this kind of small chunk of everything mixed together, then the model will say, yeah, in my previous experience with these kind of pixels, I got mixed supervision, and so here I'm going to return higher aleatoric uncertainty. And epistemic uncertainty corresponds to the case when you have, yeah, this kind of, pedestrian. I don't know exactly why it determines this pedestrian part as a high epistemic uncertainty, but this kind of tells you that the model perhaps have not seen this type of pedestrian before, but still guessing that this should be pedestrian, but I'm not too sure about that because I haven't seen this before. So this is how you interpret the results when you have a good disentanglement of aleatoric uncertainty and epistemic uncertainty. So how do we address them, right? That's the next question. And this will be addressed in the next coming lectures. Lecture 10 is about epistemic uncertainty, 11, aleatoric uncertainty, and 12, we're also going to look into the relationship between epistemic uncertainty and aleatoric uncertainty, how to decompose them. This is the research topic for Balint, actually, as well, so he's working on that. So if you also have questions, you can go to Balint and ask him as well. All right, so let's talk about uncertainty data format to begin with. So what am I talking about now, right? When you say uncertainty, yeah, we talked about different types of uncertainties, but eventually we have to deal with uncertainties in computational domain. So you have to define whether that's a floating point value or integer value or array or whatever, right? A string, right? So here we try to quantify. We wish to have some quantified definition, in other words, and for that we need to have a data format for this uncertainty. So the simplest form of uncertainty estimate we can think of is basically a scalar. So confidence value, we are going to write that as a c of x from now on. So the output is f of x and confidence is c of x. It's going to be a value between 0 and 1. It will have some written down meaning, like probability that f of x is correct. Okay, that's the simplest I can think of. What else can happen here, right? Of course, you can have more complicated data formats for that. Instead of just scalar, you can have an array of scalars, like a vector. Let's say you have a face recognition task, right? And f of x is person identity. And instead of just a single number confidence value, you may wish to understand based on which factors you have lower confidence here. Is it because I have less understanding of the hair color or the eye color or mouth shape, for example? So you can also try to factorize your confidence estimate into multiple factors, because eventually confidence value is for serving some end goal, right? And facilitating communication, right? So depending on the need, you may introduce whatever more features you wish to have. Because we talked about aleatoric uncertainty and epistemic uncertainty, we can try to introduce two values for each of them. You don't have to understand the exact formulation here, but some of the previous methods try to represent aleatoric uncertainty and epistemic uncertainty in two different ways, okay? And they say if you train the model in this way, you're going to have these two uncertainty values as a result. So in this case, you have an array of two values. In other cases, you may wish to have more distribution over a continuous space, like Gaussian in a continuous space. And in this case, your uncertainty estimate has two parts. One is the mean, and the other one is the covariance matrix, where the covariance matrix will be in a D by D matrix space. And that means now your uncertainty estimate is pretty huge. It's a D by D matrix. So that's sort of, I would say, the most extreme case of uncertainty estimate. But for basic evaluation here in our course, we stick to a scalar confidence. Okay. So given this, let's move on to evaluation of uncertainty estimate. How can you say an uncertainty estimate is doing the right job? Okay. And because we wish to have study this as a research topic, we wish to build some kind of benchmark to let people compete against each other. And for that, we need a good numeric metric for comparing different approaches for uncertainty quantification. So what do we need here? We need the confidence estimate to be truthful. We've seen that in explainability as well. We want the explanation to be truthful, right? Or sound and faithful, right? How do we quantify that in uncertainty estimation? Ideally, we want the C of x to indicate the true probability of the model making a correct prediction for that sample, okay? So in uncertainty quantification, we have a rather clear understanding of what the goal of C of x should be. It should be the probability that the model is going to make the right decision here. Okay, so now we have three terminologies here. So we have predictive uncertainty, which is encoding the chance of making the right prediction for the sample. And we also talked about epistemic uncertainty and aleatoric uncertainty. So what are the relationship between these three factors? We're going to talk about that in lecture 11, actually. We just discussed that, and then we decided to have that content for lecture 11, actually. And that's also the specialty of Balint again. So we'll leave that aside and focus on predictive uncertainty for now. The model needs to now do two tasks at the same time. So one task is the original prediction task, given x, predict y. But now the model should be good at predicting C of x well, where C of x is indicating the correctness of the prediction f of x. Okay. So we're going to indicate right L for the correctness of the prediction. It's a binary label telling you whether the model has made a right prediction. Okay. So how do we incentivize C of x to be following L, right? For that, people have long discussed how to. So we first project this problem into human words, right? First of all, and then we think about how to make some human report their belief faithfully, right? For example, we're going to ask a human to tell me what is the likelihood of rain tomorrow, right? And of course, if there's no incentive at all, the person can always report some random number, make a lie, right? Which is not according to their belief, right? So how do we make sure that the person is reporting according to their belief? So we let the subject bet on the probability of rain, in this case, Q, which is between 0 and 1. And we want the subject to be truthful to their belief. And for incentivizing people, the typical tool that we use is money. So we are going to determine how much money we are going to give to the person. Okay. Whether it's going to rain or not is a binary variable, 0 or 1 tomorrow. So we are going to find out the true y tomorrow. And based on the result y, we're going to give different money to the person. If the person is confidently wrong, then we're going to give the person less money. If the person is confidently right, then we're going to give more money to the person. If the person is less confident, then regardless of the results, we're going to give a small amount of money, maybe. That's sort of the idea for this reward function here, right? And let's say the subjects are rational, right? Meaning that they love money and they will always try to maximize money. The question is, how should we design the function S here? So I gave you a little intuition of how S should look like, but let's try to theoretically characterize this. What is the requirement for S? Okay. In this case, depending on rain or not, you're going to have reward for the person, right? So if it does not rain, then the reward that the person will get is this one, and if it rains, then the reward is this one. Okay. And the expected reward for the person is dependent on the true probability of rain and not rain. Okay. So you have to multiply with the true probabilities in each case and then sum them up. And that's going to be the expected reward. And the person will try to maximize this expected reward if they are rational. And so our aim is to design a function as such that the reward is maximized if and only if the probability Q, the prediction, the confidence level, is exactly the true probability of the rain. Okay. If you write it down in inequalities, the expected reward for arbitrary Q should be smaller than the expected reward when the Q is replaced with the true probability. So, and the equality is only when the Q is exactly equal to the true probability of rain. Okay. So that means if you maximize this metric by designing by coming with some Q, then the only way to maximize this expected reward is to report the true probability. Okay. And if a function S satisfies this property, we say S is a proper scoring rule. And this is a valid reward metric for incentivizing a person to report the true probability as much as possible. Okay. So far, so good. Okay. We're going to look into two example proper scoring rules here. So the first one is log probability. We're going to prove that this is, we're not going to prove actually, we're going to leave that as an exercise, I believe. We declare that this is a proper scoring rule. So the definition is as follows. The reward is log of Q when the truth is y equals to 1. Okay, Q is basically the task is basically using Q. You have to guess the probability of y equals 1, right? So if y is equal to 1, then your reward is 0 if Q was 1, right? Meaning that you put a full bet on y equals 1, right? Then you get reward of 0. Why do you reward 0 when you make a correct prediction? Because this is essentially not a reward, but penalty. So if Q is less than 1, right? Meaning that you make a wrong choice, then you're going to get minus rewards. Okay, you're going to lose money. That's how it's formulated. And let's say you put full bet on y equals to 1, meaning that you put Q equals to 0, then you're going to get minus infinity reward. That's quite extreme. And the opposite is true for y equals to 0. You're going to get minus infinity penalty when Q is equal to 1, whereas when you're correct, you're going to get 0 reward. Okay. So the expected reward in this case is written as follows. P of y equals to 1 if the, yeah, so that's the case when you're, when the truth is y equals to 1, sorry, 0, then your reward will be this, plus the other case. And the exercise is to show that this is a proper scoring rule. This is only maximized when Q is equal to y equals to, Q is equal to the probability of y equals to 1, okay? Okay, so with that, we move on to the second example here, where we're actually going to prove in the lecture. This is a proper scoring rule. So using this, you can probably prove the previous one. So we define the score reward as minus of the square difference between Q and Y. Yeah, this makes total sense, right? Because clearly the maximal point here for the reward is exactly when Q and Y are equal to each other, right? But to prove this, right, you first write down the expected reward as follows, and that's going to be like minus p probability of y equal to 0 times q squared, right? Because in this case y is 0, so it's minus q squared. And then in the other case you have minus 1 minus q squared. And to simplify this, we put a for the probability of y equals to 1 everywhere, and we're going to have minus 1 minus a q squared minus a 1 minus q squared. Now the task is to show that this is maximized when q is equal to a, right? And for that, we use some basic properties in continuous differentiable optimization of differential function. So the first order condition for optimality is when to find a stationary point, right? The gradient should be 0. And if you take the gradient of this, this expression here, it's basically minus 2q plus 2a, right? And that should be equal to 0. That means q should be equal to a, right? And that's only a stationary point now, but we have not proved whether that's the maximal point. And to show that's actually a maximal point, we have to kind of make an argument that this is a concave function, for example. Because if you take the second derivative, it's negative everywhere. And so this is a strictly concave function. And therefore, every stationary point should be a maximal point. Global maximum, actually. So we have now proved that the Breyer scoring rule is a proper scoring rule. Okay. So why do we talk about proper scoring rule? Because we have seen that this is a design for making humans do their best to predict the true probabilities. In the same way, we can encourage a model to choose the confidence value such that C of x is equal to the actual probability of getting the prediction right. Okay. So let's take a look at how to use this property to train a neural network model. Let's consider a binary classification task for now. And let's say the function output is a scalar between 0 and 1, indicating the probability of class A. So when the prediction is closer to 1, you're predicting A. And let's say your prediction is closer to B, then you're predicting B. So there's a midpoint here, 0.5, which is the boundary between these two classes. Oh, sorry, it should be class 1 and 0, because A and B are quite confusing. So I'll fix them. Okay, and then here, importantly, we're going to define the confidence value as something quite natural. So the confidence value will essentially be this curve here. So if f of x is greater than 0.5, you're basically taking that as the confidence value. But in the opposite case, when your prediction is closer to 0, then that also means you're increasing your confidence for the opposite class 0. So it makes sense to take the max of these two as your confidence value. Okay. So here the question is, how does the log probability scoring rule look like in this case? When your prediction is between 0 and 1, and your confidence value is based on the max probability between these two classes. So yeah, again, this confidence value is the max between these two class predictions, because 1 minus f of x is the prediction for class 0, right? Okay. And we defined L as the binary variable indicating whether your prediction is correct. So L is 1 when either your prediction is greater than 0.5 and the ground truth is actually y is equal to 1, or the other way around, right? In this case, you can encourage the model to report C of x to be the exact probability of your model predicting the right choice. In other words, the probability of L equals to 1 by using the proper log probability scoring rule. Okay, so my scoring rule in this case will be S of C and L defined as log of C and log of 1 minus C, depending on whether L is equal to 1 or 0. Okay. What I'm going to do now is to translate the equation there in terms of f of x and y, because c of x and L, these are functions of f of x and y eventually, and we understand f of x and y so much better than c and L because these are new variables that we introduced here. Okay, so to do that, we are going to split 4 different cases here, depending on whether the ground truth is negative or positive, and whether the prediction is negative or positive. So when the ground truth is negative, and when the prediction is likewise negative, then you're actually making a correct prediction in this case. So so L is equal to 1, and the proper scoring rule, log probability here gives you log of C, right? Because L is 1. And C of x in this case is exactly 1 minus f of x, because your prediction is less than 0.5. Okay, so you can write it down now as log of 1 minus f of x. Likewise, in this case, you have a wrong prediction because the ground truth is 0, but your prediction is 1. So we use this formula here, log of 1 minus c. But c of x here is actually f of x, because f of x is greater than 0.5. And eventually your reward will be log of 1 minus f of x. Okay? You do the same kind of computation on the positive cases, and you're going to have log of f of x. Eventually, what we have here is we're going to have log of 1 minus f of x when the ground truth is negative, and log of x when the ground truth is positive. Which means we can write it down as follows. The scoring rule is log of f of x when y is 1, log of 1 minus f of x when y is 0. And this looks very familiar, right? This is exactly binary cross entropy. Okay. This is a very fun moment because then it tells you that well, for this binary classification task, we have always been using binary cross entropy loss for training the model. And we never care so much about making the confidence estimate based on max probability good enough, right? But incidentally, by training it in the usual way, we were actually trying to make the model report the true probability as well. Yeah, so using binary cross entropy, we are actually achieving 2 goals at the same time. And this is something that that was not really explicitly talked about in the community, but yeah, we just came up with this during the preparation of this lecture actually. So it was quite a fun moment. So now let's dive into multi-class cases. So previously we looked into binary class, right? But what if there are multiple classes? Can you make a similar statement? By training, let's say, a cross-entropy loss on multi-class classification, are we actually doing something good for the confidence estimate? And in that case, what should be the right confidence estimate, right? So let's say f of x is now an array of probabilities for each class k. So there are k classes here. And let c of x be the max probability confidence estimate. So if there's class A, B, and C, and the max probability is on class C, then we just take the probability for the prediction of class C as the confidence value. This confidence value will then be never less than 1 over k, right? Because when it's less than k, then there should actually be another class with higher probability. Again, we define the log probability proper scoring for this c of x as follows. It's log of c or log of 1 minus c, depending on what L is 1 or 0. And here we can translate L equals to 1 as y is equal to the argmax value of f of k, fk of x. In this case, you can actually write down the c of x as the max, right? Just replacing here. And the other case as 1 minus c, right? 1 minus c is exactly summation over the f of fk of x, where k is not equal to the argmax index, okay? Okay, and you can do the simplification of this into this here, right? So the first case is when you assume that y is the max probability, and max probability is exactly here, right? So you can write this down as f large y of x, okay? And the other case is your prediction is not y, right? And you're basically summing over the predictions over non-predictions, right? And so y should be one of these summands here. And so you can separate this out like this, fy of x, and then sum over everything that is not y and not argmax. Okay, it's going to be something positive here. So this is the formulation that we have so far, and we can conclude from this that this is bounded below by log fy of x, right? Why is that the case? Because for correct prediction case, yeah, this inequality holds, of course, right? Because this is identical. But in the second case, you're summing over something, you're adding something positive here. And so inside this logarithm should be bounded from below by fy of x. And because log is a monotonic function, you can apply that on both sides and have this inequality here. In summary, you have this reward function bounded from below by log fy of x. And actually, as you know, log fy of x is essentially minus of cross entropy loss function. So by trying to maximize the reward function, we are actually, it's the equivalent to, well, actually, yeah, I should say this again. So by trying to minimize the cross entropy function, we are actually encouraging the model to maximize the reward, where c of x is defined as the max probability. Yeah, so this is cross entropy. So minimizing the cross entropy is actually the same thing as trying to maximize the reward function. So by training with cross entropy loss in general for multi-class classification tasks, we are also encouraging the model to report the two probabilities in the max probability among the classes. So far, so good. Okay. Let's talk about evaluation now. So cross entropy, we describe cross entropy as a valid loss function for predictive uncertainty. But of course, we can use cross entropy for evaluation as well. The only difference is that now we are using cross entropy for test set. In the training sets, your cross entropy values will be very close to 0 anyways. But depending on how well you're reporting the true uncertainty values for the test set, you're going to have very different test cross-entropy values depending on the models. And the lower the cross-entropy value for test set, the trustworthiness or truthfulness of your confidence estimate in terms of max probability will be much better. Okay? Because of the fact that this is a proper scoring rule. So in fact, yes, people do use negative log likelihood or cross entropy for reporting the truthfulness of confidence estimates. Yeah. It's also known as perplexity in natural language processing domain. The only difference is some of the factors that you use, like taking the expectation eventually and taking the logarithm with base 2 instead of natural logarithm. But essentially, the ranking should be the same, depending on whether you use negative log likelihood or perplexity. People use some other proper scoring rules, like Breyer score. Yeah, for better interpretability in some cases. Yeah. Now let's talk about calibration, which is very similar to what we talked about, proper scoring rule, but still different. For the sake of interpretability, some people like to use calibration rather than proper scoring rules, because if you look at proper scoring rules, these are just numbers. Like it could be a very huge number as well, like 4 point something, or it could be like as small as 0.003. And you don't know how to interpret these numbers. But calibration gives you a little bit better intuitive understanding of how good you are in terms of the truthful representation of your uncertainty. So this is called calibration, where you have on the y-axis you have accuracy, and on the x-axis the reported confidence. So what you're doing here is over the test set, you let the model report confidence levels for every instance, and then you're going to bin the test samples according to the reported confidence. In this case, you have 10 bins with width of 0.1, and for each bin, you're going to measure the accuracy of the samples corresponding to samples corresponding to this bin. And in the ideal case, if the model is super well calibrated, the first bin corresponding to confidence level 0 to 0.1, the accuracy should be close to 0.1, for example. And for the second bin, the accuracy should be close to 0.2, and so on. So what we can do is we can draw this kind of diagram like this, and then measure the difference between the perfect calibration case, where you have x equals to y line, and measure the deviation from that line in truth, in the actual histogram. Okay, so in the well-calibrated case, you're going to have a very small gap between the ideal calibration and the truth. And in the less calibrated model, you'll have this kind of plot. Okay. So how do you? So I'm going to introduce some notations to make this better quantified. So let's say x is the input and y is the output. A discrete output from 1 to k. And the model output is h of x. And yeah, in this case, I write down p instead of c, right? It's essentially the same thing. So we say the model h has a perfect calibration when the probability of making correct prediction for the samples where the confidence level is at a certain level, P. The prediction accuracy should be close to P for every P between 0 and 1. Okay. So sounds good, but how do you quantify that? Okay, so this is another way to say that in example. So prediction for any sample in your data set with confidence score equals to 0.8 must be correct 80% of the time. So that's kind of frequentist meaning of this calibration. So there's something called ECE, which is essentially measuring the deviation from y equals to x line. So this is step-by-step procedure for computing this score. 1, train the network. 2, make predictions on the test set. 3, you group the predictions into m different beans, and the bean is defined in such a way that there are large M different beans, and the beans are where you collect samples with certain level of uncertainty between small m minus 1 over m to small m over large M, right? And then you're going to measure the accuracy on that bean, right? And you're going to measure the confidence over that bean. So you can also take the midpoint of the bean as the confidence here, but to be more precise, you can also take the mean of the confidences for the samples here. And you take the difference between the two, and of course you're going to take, depending on the bean size, you're going to reweight each bean differently. And that's going to be your EC score at the end of the day, okay? So in a way, we're kind of approximating the perfect calibration here by first of all taking the difference between the perfect calibration minus the true perfect calibration and the true, confidence, true accuracy on the confidence bean P, and then take the expectation over different P values here. And then we're going to discretize it, because if we have continuous beans, then we're not going to have any sample in many of the beans. So yeah, this is ECE. We have ECE here, expected calibration error. Some people also prefer to use maximum calibration error, which is basically measuring the max difference between accuracy and the confidence level across beans. Okay, so this is kind of the worst case calibration error. There are several drawbacks with ECE metric. One could perfectly game the metric. It's not a proper scoring rule. That's why you can game the metric and introduce strategies to achieve really good ECE score like 0, even if the model is not reporting the true predictive uncertainties. And you can think of different strategies in exercise 3. That's part of the exercises. Yeah, this is the reliability diagram, the plot that I showed you before. And ECE is measuring the average gaps here, and MCE is measuring the maximum gap. So you're beware that you're not taking a vanilla average here, but you are taking weighted average based on the size of the beans. Okay, so the reliability diagram could be a little bit misleading as well, depending on the deviation of bean sizes. Okay, so far we looked into different evaluation tools. One is proper scoring like NLL or Braille scoring. There are calibration metrics like ECE and MCE. Okay. So this is a small kind of small section on in practice how well calibrated are deep neural networks. Essentially, the models are trained with proper scoring rule anyways, or some lower bound on proper scoring rule. So they are expected to give you very good uncertainty estimates. But that is not the case because like even if you train the model with a loss function, which is supposed to give you very good training set accuracy, when you move to a test set, does not generalize super well. Likewise, the same thing happens with uncertainty estimates. So in practice, on test sets, the uncertainty estimates are not perfect. So we have two different cases here. The left is LINET, which is a 5-layer, very small. And on the right is about 100-layer ResNet. And ResNet tends to give you less well-calibrated uncertainty estimates. Why is that? So they did quite a bit of analysis on which factors make the model less well-calibrated. Okay. So they looked into depth, for example, and then width. Depth seems to increase the ECE a little bit, right? While prediction-wise, the error is going down with increased depth, right? ECE-wise, it seems to aggravate the calibration. Likewise, width is decreasing the error quite quickly, but you're increasing the calibration error. Okay. And also, if you train it for a long time, right? Test error is showing a bit of overfitting here, right? But eventually, when you decrease the learning rate here, you're converging to more stable regime. But calibration-wise, in this case, measured in terms of negative log likelihood, the error is actually moving up as you train more than too much. So, but beware that this is not something that's universal. That happens sometimes not. So it's not something fully generalizable. And I wish to talk about temperature scaling for a bit to give you a simple fix for calibration error. Okay, so let's say you're not happy with the calibration error on the test set. What you can do is you can introduce a bit of changes in the way the model outputs the final probabilities. So let's say the final layer of your prediction is a softmax layer. And you can actually control the temperature of the softmax to let the model report the confidence level with varying degrees of sharpness. So when the temperature is high, then the model will likely generate high entropy outputs because everything will be close to 0 after dividing through by temperature. Whereas when temperature is lower, like close to 0, then your post-softmax outputs will be close to 1 hot. So your confidence values will be overconfident. And depending on your needs, you may need sometimes underconfident models or overconfident models. And maybe being a little bit less confident or overconfident will help you be better calibrated at test time. So you can solve an optimization problem of optimizing your ECE value on the test set by tuning your T a little bit. So with different T values, you're going to measure ECE multiple times. You can do grid search like that, or you can do, if you like, Bayesian optimization or some, if you have some assumption of like unimodality of the function, then you can also try to do some kind of, I forgot how it's called. You do Fibonacci search, if you know what this is, like you can optimize 1D unimodal function very efficiently with that. Anyway, so you can improve ECE like this as well. This is showing the effect of temperature scaling when temperature is 1, your ECE values are like this, but some of them are easily fixed, like this huge value like 16%. These are decreased to 1.26% just by scaling the temperature. So this is a cheap solution for having better calibration. More recently, at NeurIPS 2021, people have reported that more recent versions of models like VITs and mixers, MLP mixers, they tend to have a good calibration as well. If you're interested, you can also go to the paper and read it. I have some more materials today, but I'll stop here and resume from here next time, which is in a month.